With today's contents or the main contents of this webinar. So this webinar is broken down into 4 parts. So firstly, we'll be taking up the slope stability analysis, followed by seepage, then the ground deformation analysis, and then the consolidation. So the slope stability or the determination of the factors for the slope stability is very crucial for the embankments which are created during the constructions or the excavations. And the slope failure occurs usually when the shear stress which is imposed either due to the additional surcharge loads, pore pressures, or the seismic loads above the self-weight of the slope. When it exceeds the material strength of the slope, then you will experience or you will observe the slope failure. So the methods for the analysis of slope stability, they are of 3 types. So first one could be the limit equilibrium, then the strength reduction method, and then the last one is the stress analysis method. So these two are the finite element based. So the limit equilibrium method is based on the equilibrium of forces and slices or the moments in the slices, and the accuracy of the results from the limit equilibrium analysis. It depends on what parameters are using for the ground material, the geometry of the slope, and the analysis method chosen. So in the literature, there are different analysis methods have been proposed based on how they solve the indeterminate problems for the slope stability. But amongst them, the Bishop method is most widely used because of its simplicity and accuracy, and is also applicable for the arc and non-arc failure surfaces. So as you can see in this expression here, the factor of safety for the Bishop method is determined using this expression, and this expression requires an iterative procedure. So you start with an assumption of an initial factor of safety, and then you iterate it till the solution converges theoretically. Then the second method is the strength reduction method, which is based on finite elements. So it uses the constitutive relations for the ground material, and it satisfies the force equilibrium all around in your model. And the main advantage of the strength reduction method is that unlike the limit equilibrium method, you don't have to assume a failure surface. And in this method, the strength of the material, which is described in terms of C, the cohesion and the internal friction angle, it is reduced until the divergence occurs in the model. So the factor by which the material strengths are reduced, that is your factor of safety. So it is described in this expression here, as you can see. So the final cohesion and the friction angles are described in terms of the initial cohesion and friction angles divided by the factor of safety. So the factors, there are a number of factors which may affect the results which you will obtain from the strength reduction analysis, and the results might differ from the limit equilibrium analysis solutions. So the number of factors include the number of elements in your model for the finite element mesh and order of elements, whether they are linear elements or second order elements. So usually second order elements are preferred to obtain good results. Then the stiffness or the elastic modulus for the grounds and the reinforcements. So depending upon how stiff the ground is and what is the relative ratio between the ground and the reinforcement, the deformations in the ground will vary. Then the third one is dilation. Dilation, if you keep a dilation value of 0, then you're making the deformations in the ground very restrictive. But if you will keep a dilation higher than a value of 0, and it can't be more than the friction angle, so then you will experience a more higher magnitude of deformations. So you will have to check for this parameter as well. Then the constitutive relation, how the stress and strain developed in the material is related. So the different constitutive laws, they might give you different factor of safety, but traditionally Mohr Coulomb is widely used. And then also for solving the nonlinear analysis, as you might be aware that Mohr Coulomb is a nonlinear material model. So it requires iterations. So depending upon how the solution is converging, whether it's converging based on force, displacement, or energy, or the strain energy, the accuracy might be affected. So for the case study, in the first benchmark is a homogeneous slope here, which is unreinforced, and you can see the material parameters given here. And so firstly, I would just like to show you the this problem within the SoilWorks. So I'll just drag in the window from the other screen, and you can see the grid defined here. So this is your slope. So you can also check the material properties. So you can see the material properties as it was shown in the presentation. And you can also see the grid here for determining the failure surfaces. And the analysis of this model has already been done. So we are moving to the post-processing part. So you can check the factor of safety for your failure surfaces. So for this point, you can see the factor of safety, and you can also adjust the contour properties. So if I just double click on this surface, this will show the failure surface in this region, and double clicking on any slice would give the material parameters, the weight of this slice, and the forces all around it. So this is the free body diagram. So in this case, the factor of safety has been obtained as 1.272, and we also derived a formulation based on Bishop's method. So starting from the factor of safety as 3 here, in the next iteration, the factor of safety was obtained as 1.5, and then I can use this value to iterate my solutions. So as you can see on the screen, the solutions can be iterated. So we are nearly close to the solutions. So this is the solution has converged from the theoretical expressions for the Bishop method, and it's equal to the value in the SoilWorks or the software. Then just as a second verification, we also have done the finite element analysis. So you can see the finite element mesh here using the same material properties, and we just have defined the supports here. And after the analysis, the factor of safety is 1.28, slightly higher than 1.27, but its accuracy is good. And in terms of the failure surface, since we are not assuming the failure surface, the software computes it automatically. And you can see the development of the failure surface here using the maximum shear strains. So this profile matches exactly what you saw in the through the limit equilibrium analysis. So I will just close this one, which brings to an end of the part 1. Then moving on to the part 2, which is the seepage analysis. It is based on Darcy's law for saturated and unsaturated soil. So for the unsaturated soil, the Darcy law is modified, and the analysis can be performed both for the steady state and the transient state. And sometimes your soil might not be fully saturated. So in that case, the unsaturated behavior in the soil invokes the requirement of the nonlinear seepage. And for the nonlinear seepage, or also for the linear seepage, you can use a variety of elements such as triangular or quadrilateral, and it could be linear or second orders. So at the nodes of these elements, the the pore pressures will be calculated. And when you're performing the transient analysis, it is well known that for this solution, you need to know the initial boundary conditions for the analysis. So those are derived from the steady state. So generally for the seepage, for transient analysis, first you do the steady state solutions and then you proceed towards the transient analysis. And if you have unsaturated soil behavior, then they can be represented in terms of different soil water content curves. So they could represent, for example, a relation between the relative permeability and the suction pressures. So in the literature, there are different types of curves which you can use. And the type of boundary conditions which can be defined for the seepage analysis involves total and pressure heads at the nodes, and the flux, the influx or the outflux. And the last option or the last boundary condition is the seepage phase, or we also call it as the review boundary conditions. So this boundary condition is very helpful in calculating or in knowing the phreatic surface due to an unconfined flow. So for the verification here, we used a problem which was proposed by Muscat in his paper. So the geometry of the problem can be seen here. So we have steady state boundary conditions on the right side and the left side of the model. And so we can use the total pressure conditions here. And then the problem involves the determination of the seepage, where the seepage will occur on this face AD. And since the soil would also behave as an unsaturated above this phreatic surface, so an unsaturated property function in terms of the soil water content curve will also be used. So you can see this function here, which is a function of relative permeability and how it varies with the suction pressures. So I'll just take you to the seepage part. So you can see the mesh here representing the ground material property. And the unsaturated property functions can be defined as well. So you can see you can define different types of functions in terms of Gardner frontal functions. So mostly the Gardner and the frontals are widely used. So we have defined it here. So the relative permeability has the ratio of 0.12 from a fully saturated state, and the suction pressures or the limit is 0.001. And once you define this, you can define the boundary conditions, the total head boundary conditions of 3.22 meters on these nodes to the right and of 0.84 meter to the left. And once these are defined, you can also assign the seepage phase boundary conditions at these nodes. So here the software will use iterative algorithm to determine the phreatic surface. And once the analysis is done, you can see the different types of results in terms of total heads, pore pressures, and the phreatic surface. So this blue line here represents the phreatic surface. So if you check this value is determined as 2.12 meters, and from the monograph proposed by Muscat, it's 2.08. So a slight marginal difference. So, and before we proceed to the third part of our webinar, I would just like to show you the analysis of an embankment, how you can do it in the SoilWorks environment. So you can see an embankment here, and in a similar fashion you can define, so this is more like a commercial problem. So you can define the pressure head values here, total head values, and you can define the boundary conditions here where you want to obtain the phreatic surfaces. And once the problem is analyzed, you can check the results. So you can see that this would be the phreatic surface in the steady state solution and is lying within the embankment, so your embankment is safe. So in this way you can perform the more complex commercial applications using these basic concepts. Then in the third part, for the ground deformation analysis, the soil structure interaction analysis can be performed for both the static and the dynamic loads. And for performing the deformations in the structural members, they can be analyzed either through the limit equilibrium solutions, or you have the pseudo FE solutions, finite elements, and the finite differences. But the limit equilibrium solutions are handicapped in a way that they can't give you the deformations within the soil itself. They might give you the deformations and the forces in the structural members, but not in the soil. So to get the full picture in the analysis, you need to perform soil structure interaction analysis either through the finite elements or through the finite difference methods. And the static analysis can be described either in two forms. It could be the linear or nonlinear analysis. And the nonlinear analysis could occur either due to the nonlinearity in the material, or the geometry if there are very large strains in the model, or the boundary conditions if there are if there is some separations, or if there is a gap occurring between the elements at the boundary, then the nonlinearity could be because of that as well. So generally in the geotechnics, the material nonlinearity can be modeled through the constitutive equations. So you have different types of material models, such as in terms of you have the Mohr-Coulomb, the modified Mohr-Coulomb, which can model the hardening of the soil, the Hoeken-Brown material models. So all these different models have different formulations pertaining to different type of soils and rocks. And in terms of modeling the boundary nonlinearity, you can either use the interface or contact elements for the full soil structure interactions, or you can also create links with some material stiffness between two nodes, or you can also assign springs with stiffness values. So for the analysis, we created a case which was presented by Giroud in his paper. So this problem is of a smooth rigid footing which is resting on an elastic ground. So you can see the geometry of the problem here. And since the problem is symmetric, so we will only be modeling only half of the model within the program. So this is how the half model looks like. So the material properties you have seen, and if you notice here, then since we will be expecting a larger value of formations in this region, so we have meshed it fine, and as we proceed towards the boundary, we have kept a coarse mesh. So this you can control through the seeds. And in terms of load, we have assigned a prescribed displacement load. So all these nodes at the top, they are allowed to displace in the vertical direction by 10 millimeters. And in the post-processing, if you go, let me just hide the loads. So you can see the development of the results. So you can check in with bands as well, and you can check the results in the different formats. So as you in this case, the load is applied in increments of 10. So let's just jump into the last stage. So you can see the results as well for the last stage. And you can see the mesh as well. And if you want to check the results at any nodes, then you can tag it as well. Now to obtain the reaction on the surface, what you have to do is that you need to get the reactions or the vertical reactions like this, as you can see. So once this reaction is obtained, and you will see here that there will be a slightly higher value of punching beneath this footing. So these reactions can be summed up in an Excel and uh, can be obtained to obtain, or can be used to obtain the bearing capacity on this soil. So from these expressions from the theory, uh, the the reaction is computed as 15.15 kilonewton, and in the SoilWorks, what you saw in the program, that was only half of the reaction. So if you double those values, the results will come out to be as 15.37. So this is for the full footing, and this is also now for the full footing. So as you can see that the results are in have a very marginal value of error. So they are in good approximation. Now going on to the second part of the session, which is the consolidation. So the consolidation or the mixture analysis relates the excess pore water pressures with the effective stresses. And as the soil is loaded, the initial load is repelled or is taken up by the pore pressures or the excess pore pressures which develop in the soil skeleton. And when they dissipate, they transfer the load to the soil skeleton. And as a result of that, the soil tends to displace or move towards in the direction of the gravity. So the consolidation problems can be analyzed either through the analytical equations or with the finite elements. And when you're using the finite elements, then you can assign the different boundary conditions, such as draining conditions. It means that the pore pressures at those locations will be equal to the zero. And if you want the structural components in the model, or if there are other components such as sand which do not consolidate, then you can assign them non-consolidation conditions. And at the end of the analysis, you have to make sure that the pore pressures at the draining boundary condition, they are equal to the zero. And there are a variety of elements which are supported for the consolidation analysis. So it could be a 3-node triangle, 6-node triangle, higher order, a 4-node quadrilateral, or an 8-node quadrilateral. And this is a case of a one-dimensional confined compression. So the boundaries, so we have an homogeneous sample, and the boundaries here are considered as smooth and frictionless. And we applied a uniform pressure at the top of the piston, and then the soil is allowed to compress. And then we have this filter here for the dissipations of the pore pressures. And the solution to this type of problem was given by Verigit using this expression. So this expression or this analysis can be modeled within the program as well. So I will just take you to that problem. So you can see this is a simple mesh of 1 by 1 meters, and for this analysis, the material was assumed as elastic ground and without any weight. So we're not calculating any stresses due to the self weight. We are just concerned with the pore pressures and how they developed as the additional or the external load is applied. And in terms of the boundary conditions, the model or the sample is confined to displace in the horizontal and the vertical directions. And at the top of the sample, the pore pressures are allowed to dissipate, and hence we are assigning a draining condition here, as you can see. And in terms of the so this model is created in different construction stages. So in the first stage, you only initialize the model, and then in the second stage, an external pressure load is added, which can be seen here, which is this piston load of 1 kilopascal. And then in the third stage, the excess pore pressures which were generated, they are allowed to dissipate. So you will be seeing deformations in the third stage onwards. So in the results, in the ground element stresses, you can check the results for the excess pore pressures. So let me just show you the first stage and it will make it more clear. So in the initial stage, when there is no external load, so the excess pore pressures developed are equal to 0. And when we move to the next stage, where the load of 1 kilopascal is applied, so the 1 kilopascal load is all taken up by the development of the excess pore pressures in the soil. And then in the third stage, we allow the pore pressures to dissipate and consolidation will happen. So you can see the results they start varying here. So at these top nodes, the pore pressures, they will also always be 0. So this is for the element, and if I show it for the node at the top node, so the pressure will always be 0 at the top node since you assigned a draining condition here. And you can also tag the results at the different nodes and check the different pore pressures as they develop. So as you move with the different stages, you can see the pore pressures, it tends to get 0, and you can see that the consolidation has fully occurred and the pressure or the 1 kilopascal pressure, additional pressure or the load, is now fully taken up by the soil skeleton. So this is the basics of applying the boundary conditions for the consolidation analysis, and you can use it for the commercial projects as well, such as if you have an embankment constructions on a soft soil. So in this model, you have different layers of clays and sands, and you can check the material properties. The last layer is of the rock, and then we have to construct an embankment on this clay layer. And we can also simulate the effects of drains, which can accelerate the consolidation by assigning the draining boundary conditions within the model. And since the embankment won't be consolidating, we can assign it as a non-consolidation boundary conditions. And we can check the constructions, the full construction sequence during the consolidation from the initial stage till the long leaf time. So again, I can show you the results for the pore pressures, which is the initial stage. So they will be 0. And then as you construct the embankment, the pore pressures, they will start to develop due to the presence of the external load. And as the time proceeds, the pore pressures again, they will dissipate due to the presence of the drains. And finally, in the long-term analysis, they will be negligible. So this was the basics of how to use the boundary conditions for the consolidation analysis, and how you can use it for a commercial project as well. So if I take you back to the presentation, so the solutions which were obtained by solving these equations for the different time steps and at the different depths in the model, and the results obtained from the SoilWorks, they are in a good match, as you can see from this graph. So this was how you can, this was the introduction on how you can do the finite element and the limit equilibrium analysis for your slope stability problems, seepage, whether it's a steady state or transient state, ground deformations using the finite elements, and consolidation using the finite elements within the SoilWorks work environment. So we have a next webinar on 31st where we'll be using the concepts which you have learned in this session, and we'll be tackling more advanced problems in terms of slope stability using the reinforcements and the change in the boundary conditions for the water level and how they overall affect the factor of safety for the slopes. So that is the next webinar on 31st.